All right, so in this video, we are going to go over the gas laws and how to use them in some of these different math equations. So you are going to need your calculator. You're going to need to print out this note sheet, and you're also going to need this gas reference sheet right here. Okay, so all that can be found, well, except the calculator, can be found on the Canvas page. All right, so just a quick heads up. So we're moving over to the right side of this reference sheet, and we are going to tackle some of these more basic gas laws that we sort of reviewed in class when you did that little simulation. So what we're going to look at today are these gas laws right here. So we're going to look at how to use these in some of these gas law problems. Okay, I'll give them to you on the sheet, but they're also right there on your reference sheet. All right, so it's good to know where it is, just so we know how to use that. Okay, so I'm going to jump right into the first one, section 11.4, which is Boyle's law, pressure volume. So we talked about the fact that these are the only two variables that are inversely related. Hopefully you can see by the graph that they are inversely related. We did that little simulation where we graphed it. Some of you guys came up with this real-world example of a bike pump. As the volume of gas inside this cylinder here, as it decreases, it actually increases the pressure of the air inside there. That's how a bike pump works. All right, so the formula for Boyle's law, again, which is right off of our reference sheet, looks like this: P1 V1 equals P2 times V2. So here's an example problem. It says a gas has a volume of 5.7 liters at a pressure of 3.2 atmospheres. What is its volume at 4.7 atmospheres? So if you think about this for a second, I initially have a pressure of 3.2, and I'm increasing the pressure to 4.7. So the pressure is going up. So what should happen to the volume? It should go down if these are inversely related. So I should see a number that's less than 5.7. So let's see what we get. The best way to do all of these gas law problems is to write out what you have, what's your given. Okay, so a gas has a volume. So what I'm going to do is I'm going to try and keep these all straight by saying that's my V1. Okay, that's my volume 1, 5.7 liters. At a pressure P1 of 3.2 atmospheres. Okay, and then it says, what is its volume? So V2, question mark, when the pressure is 4.7. So my P2 is now 4.7 atmospheres. Okay, so I have all the given and what I want to find. Now I'm going to come over to the formula. Now I gave you the formula right here, but what you really want to do is you really want to look at which formula should I use from the reference sheet, because that's really the question that everyone loves to ask. How do I know what formula to use? Well, write out what you have and just look at all these formulas here. I have a P and a V. That means I'm going to be using Boyle's law right here. Okay, so now the formula P1 V1 equals P2 over V2. What I want to do is rearrange this equation to make it a little more useful for me. Okay, you can plug the numbers in and solve it that way if you want, but I prefer to move the equation around with its letters because it's a little bit easier. So I'm trying to find the V2. So I want V2 by itself. So I'm going to divide both sides by P2. And then I can cancel out this P2 and this P2. And now I have my new formula here. My new formula says V2 equals P1 times V1 over P2. Okay, so now I can just plug these numbers in. So I'm going to have two numbers in the numerator and one in the denominator. So my P1 is 3.2 atmospheres. My V1 is 5.7 liters, and my P2 is 4.7 atmospheres. Okay, if you notice, atmospheres is in the numerator. It's also in the denominator. Those cancel out. Now I'm just going to do 3.2 times 5.7 and divide that by 4.7, and I should get 3.9 liters. I know what my unit is because it's the only unit that did not get canceled out. Okay, so when you're showing all your work, you got to have the numbers, you got to have the units, you got to have the formula, everything that I just showed you. This is what the homework should look like. Full credit will be given for all the work that is shown. Okay, so don't just give me an answer and say I put it in my calculator. That doesn't work. Okay, the next one, Charles' law, volume and temperature. Well, again, we talked about this in class. If pressure and volume are the only two that are inversely related, then everything else has to be directly related. And if you look at the graph, you can see there is a direct relationship between these two things. Okay, some of you guys said this in the real world example. If I take a balloon, I put it in the freezer, it's going to get smaller. If I put it in boiling water, it's going to get bigger because temperature and volume are directly related. As one goes up, the other goes up. As one goes down, the other one goes down. Our formula looks like this. It's V1 over T1 equals V2 over T2. Okay, so here's another example. A balloon is filled with helium gas and has an initial volume. So again, my V1 is 88.2 milliliters and is heated to a T1 temperature of 35 degrees Celsius. Okay, now here's the trick. With all of these gas laws, your temperature has to be in Kelvin. So it has to be in Kelvin. You cannot, it won't work if you leave it in Celsius. That's the most common mistake, is leaving it in Celsius. So I need to add 273 to turn this into Kelvin. And when I do that, when I add 35 and 273, hold on, 273 plus 35, I should get 308. Okay, 308 Kelvin. Okay, so it's heated from 35 to 155. So my T2 is 155 degrees Celsius. I'm going to do the exact same thing. I'm going to add 273 because I need to convert this to Kelvin. When I do that, I get 428 Kelvin. Then it says, what is the final volume? What is my V2? Okay, so again, my formula is V1 over T1 equals V2 over T2. I'm trying to find V2. This is what I want right here, V2. So I'm going to multiply both sides by T2 so I can get V2 by itself. So numerator, denominator, that cancels out. My new formula is T2 V1 over T1. Okay, so now I'm just going to plug those in. So I've got 2 in the numerator, 1 in the denominator. So T2 is 428K. My V1 is 88.2 milliliters. And then my T1 is 308K. All right, now in this one we can do the same thing. The temperature is going up. If these are directly related, that means the volume has to go up. So it should be bigger than 88.2 if we're doing this right. And then again, the kelvins cancel out. So what we're left with is milliliters. That should be the unit for my answer. Okay, so now I'm just going to do 428 times 88.2, and I'm going to divide that by 308, and I should get 122.56. I'm going to round that to 3 significant figures, so I get 123, and again, the units should be milliliters, because that's the only thing that didn't cancel out. And we already predicted the temperature is going to go up, so the volume should go up, and it did, so that makes sense. All right, one last one. Now we have the combined gas law. Just like it sounds, now we're going to combine these gas laws together, okay? So it looks something like this. A sample of gas has an initial volume, V1, of 2.40 liters. It has a pressure, P1, of 855 millimeters of mercury. And then it has a temperature, T1, of 298 K. So it's already in Kelvin, so that's kind of nice. Don't have to convert. All right, if the gas is heated to a temperature, so now we have a new temperature, which is 387 K. And it's expanded, so now I have a new volume of 4.10 liters. What is the final pressure? So what is my P2? Okay, and they want it in millimeters of mercury. So that's nice because this one's in millimeters of mercury, so I don't really need to do any converting. However, when I get my answer in millimeters of mercury, I do have to convert it to pounds per square inch because it wants both. Okay, so my formula, again, what formula do I use? Well, I have a V, a P, and a T. And I know it says it right here, but again, you're only going to get your reference sheet. So if I have a V, a P, and a T, I know this is the formula I need to use, that combined gas law. So I'm going to put P1 V1 over T1 equals P2 V2 over T2. They are combined together. Now, if I just do a quick, I know a lot of people like to do this where they just cross multiply and divide. So if I did that, I would come up with P1 V1 T2 equals T1 P2 V2. So I just cross multiplied both of those together. I want to get P2 by itself. So that means I'm going to divide both sides by T1 and V2 so I can get that on its own. So T1 V2, so I can cancel that out. I can cancel numerator, denominator. And now I just have P2. So P2 equals P1 V1 T2 over T1 and V2. All right, so it gets a little more complex here, but you just got to keep everything straight, and then it's usually pretty straightforward. Okay, so I'm going to plug in my P1, which is 855 millimeters of mercury, mmHgs. My V1 is 2.40 liters. My T2 is 387 K. No converting necessary. And then let's see, T1, 298 K. So there's the kelvins that cancel out. Cancel, cancel. And then what's left? V2. So what's that? 4.10 liters. And now my liters cancel out because it's numerator, denominator. The only thing that's left is millimeters of mercury. So that's what my unit for my answer is going to be. Okay, now I just need to multiply everything on the top, divide by both of these things. Don't forget to put the bottom in parentheses, so you multiply those two together before you divide, and you end up with 650 millimeters of mercury. Okay, now 650, the only problem here is that only has two significant figures, but we need three. So the easiest thing to do here would be to put a decimal right there. All you scientific notation fans, if you want to do it that way, it would be 600 or 6.50 times 10 to the second millimeters of mercury. Okay, so there's our first answer here. Now it also wants to convert this to pounds per square inch. So I'm going to rewrite this and I'm going to convert. So on your conversion sheet, it says 760 millimeters of mercury equals 1 atmosphere. Okay, so then I can cancel that out. And then atmospheres, I can go from atmospheres, ATM, to PSI, or pounds per square inch, and it says 14.7 pounds per square inch equals 1 atmosphere. So I can now cancel that out. So I got to use a little dimensional analysis to convert my answer to pounds per square inch. And when I do that, I should get 12.6 pounds per square inch. Hopefully that was helpful.